Hello, welcome to the Rock Cycle Lab video presentation. Let's start with talking about Yosemite Valley in California. The valley formed when rivers carved through granite rock over thousands and thousands of years. But what actually is a rock? And what's a mineral? Well, if we look at the image on the right, that's a zoomed in section of rock from Yosemite Valley, granite. And notice all of the different colors. There's black flecks, gray, brown. So clearly, this section of rock is made up of different sorts of chemical compositions, different bits of minerals, we can say. So rocks are actually made up of multiple minerals. But what's a mineral? More precisely, it's a naturally occurring solid with an ordered internal chemical structure, meaning that it's homogeneous throughout. So here's an image of a diamond in the rough. So the diamond is actually in the center here, the clear crystalline compound. So this diamond is a great example of one mineral being present in the surrounding rock, which could be composed of many minerals itself. So the key point here is that rocks are composed of multiple minerals. And we're going to be focusing on rock formations throughout this lab. So to start, we have to cover what the three main types of rocks are: igneous, sedimentary, and metamorphic. Those may be familiar to you. But to start with igneous, like the name implies, ignite, fire, the root word means that it comes from magma or lava, molten rock. So as these rocks cool, they become solid, or I should say as the magma cools, it becomes rock, solid. And it can cool very quickly or cool very slowly. And we can call the rate of cooling and the rocks that those form extrusive when they cool very quickly, or intrusive when they cool slowly. This diagram does a good job of showing how that could happen. Extrusive igneous rocks are formed when magma becomes lava on the surface and it cools in the surrounding air, which is much cooler than the magma chamber that the magma could have been sitting in for some time. And that's opposed to igneous rock formation, which is when magma cools very slowly because it's insulated by the surrounding crust or upper mantle of the earth. So the surrounding rocks would act as insulation to help slow down that cooling. But what does that really mean for the properties of the rock? Well, this rate of cooling defines and governs how large the crystals in that rock could become. So, for extrusive rocks that cool very quickly, they have fine-grained crystals. And that's opposed to the intrusive rocks, which are coarse-grained. They have larger grained crystals. Larger crystals could be very easily noticeable by the naked eye, because those crystals take time to form. They have to have constant temperature or pressure for the chemical interactions to happen and for crystals to grow. Remember that it takes time for crystals to grow, so when they have more time, i.e. when intrusive rocks cool slower, crystals get larger. So that's one way to differentiate them, igneous rocks. Now if we think about what the dominant chemicals, molecules, atoms would be in those rocks. That also is a good way to differentiate them because in felsic igneous rocks, they're often more light colored, they are less heavy, less dense, and they have lower melting points. And the word felsic actually comes from feldspar or silica that predominantly make up felsic materials, felsic rocks, as opposed to the other end, mafic, basically the opposite. They have more commonly dark colors, they're heavier, much heavier sometimes, i.e. more dense, and they have high melting points. They often contain heavier elements like iron, magnesium. And of course, like everything in nature, nothing is black and white. There's an intermediate category as well, where there could be some felsic minerals and mafic minerals, like this diorite in the center. So now we know that igneous rocks could be broken up into categories by their crystal size and by their colors or their density. And those things can tell you about the history of the rocks themselves, how they formed, what they might contain. And remember, igneous rocks are, I think, the most straightforward in that they are simply cooled magma, or they cooled from lava if they were extrusive. At one point, all rocks were molten. Could be billions of years ago. But we have two other categories, sedimentary and metamorphic. Let's now go to sedimentary. Like the root word, sediment implies, these rocks could form from depositions or sand, silt, or clay that might be picked up, like in water or in the air as dust. And then that sediment is deposited, such as on the bottom of the riverbed or the ocean, or just simply on the surface of the ground. And then, to actually become a new rock, they have to go through a process called lithification, which involves compaction and cementation. Compaction is simply being squished down so that the pores or spaces between the particles get smaller and smaller and smaller. This is often due to the weight of whatever stuff is above that sediment. Could be water, such as at the bottom of the ocean. There's a ton of pressure from the water, or the weight of the water of the riverbed, but especially the weight of any more sediment that gets deposited on top. And now let's talk about the term clast, which basically just means the particles or little bits of stuff that make up the sedimentary rocks. They could be pebbles or very fine grains of sand or organic material like deposited shells or skeletons of animals. This could go on and on and on. Clast could be made up of lots of different things. But when they undergo compaction and cementation is when they become sedimentary rocks. Now let's go back to the process of cementation. So between these clasts, in between there's pore space, air or water, and after compaction that space gets smaller and smaller. And water could flow through these pores until it gets to a small enough point, but that water carries with it very, very small particles that actually get in between those pores and could act like glue. So think of cement like for the roads. They start with a very coarse material like ground up rocks from other cement or just from straight rocks from the quarry, and then they fill the gaps in between with something that can glue all those particles together. So cement could be a good example of a man-made sedimentary rock. Sedimentary rocks are really just for naturally occurring rocks, but I think the formation of road cement is a great way to think about it. Sedimentary rocks are also really cool for geologists to learn about the history of the formation of planets or landscapes. This image is actually from Mars, and notice these horizontal layers or strata that you can see on this cliff. Logically, the layers at the bottom had to form before the layers more near the surface or the top. So if you look at a cliff like this, you can work your way down the various strata, analyze the chemical or structural compositions of those layers, and then you can understand things that relate to climate, atmosphere, paleobiology. They're making new discoveries every day, it seems, from analyzing the strata, just from analyzing the rocks. Okay, now we're to our third main category of rocks, the most complicated, I would say, metamorphic rocks. Like the name implies here, metamorphosize or to change. These rocks started out as igneous, sedimentary, or even another metamorphic rock, and then metamorphosize and become a new kind of rock. Here's an example of one system of metamorphism. We're starting out here with shale, very common in the eastern United States, such as Pennsylvania. It's a sedimentary rock, shale, and it's formed from compressed bits of mud and clay, and it breaks apart very easily into these flat sheets. Now, once the shale undergoes enough heat and pressure for enough amount of time, it can progress from shale to slates, to phyllite, schist, and finally gneiss. Now, to get to these last stages of metamorphic rock, it takes such intense heat and pressure we can hardly even comprehend. The slates and phyllite has to be buried, thousands and thousands of feet underneath the Earth's surface to be under so much weight and for it to get so hot to actually form these later stages. But gneiss is very common on the surface as it becomes pushed back up to the surface that we can make countertops out of it. So this metamorphism that changes the rock's composition causes the rock to become almost molten, but not quite. It causes the rocks to form ripples or twists, squishes down the rock so hard that we can get these foliation types, these bands of different colors you might see, such as on this gneiss here. You can see these lines, which your first thought might be, oh, these are layers or strata from sedimentary rocks, but actually, because this is a metamorphic rock, it has foliations. So the changes that actually cause a metamorphic rock to form can alter its chemical properties and its physical properties. The physical properties are the most obvious. They become flattened. Patterns can be formed in the compression to make linear or these foliations of these different layers. So there's that word again. And the chemical properties, you could take a whole course on that alone, but basically it can change the crystalline structure, or it can cause different chemical compounds to form, chemical reactions take place. But the overall thing that's required for metamorphic rocks to form is crazy high temperatures and pressures for long enough periods of time. So other igneous, sedimentary, or another metamorphic rock would have to get buried deep under the crust to form a new kind of metamorphic rock. And that's happening at every point in time, right under our feet. Rocks are being buried, such as due to subduction of tectonic plates, which we haven't learned about yet, but we will later in the semester. And then these metamorphic rocks might come to the surface, again through tectonic activity or volcanic eruptions. So this metamorphism happens deep under our feet at all points in time. And these metamorphic rocks may be brought back up to the surface due to geologic uplift, or by the rock on top being eroded away, exposing metamorphic rocks. That's how we can see them, even though they took crazy heat and pressure deep underneath the ground to form. Another point that is very important to understanding rock formation is that the parent material, i.e. whatever stuff was originally there to make the rock, is extremely important to the final rock that's going to form. So obviously you're not going to have the same sedimentary rock from sand versus from seashells or compressed bits of algae. Same thing is true for metamorphic rock or igneous. If you have a different starting material, you're going to get a different end result. Here are a few different textures of rocks that could be useful as you collect a rock from around your area, which will be your at-home assignment in the lab this week, is to simply find a rock, make sure that it's not from cement, or if it's from poured rock, like a bit of cement or asphalt. And then you should observe this rock's physical properties. Does it have crystals? What color is it? How hard is it? Can it scratch objects of known hardness? The directions are in the lab assignment. And you will most likely not find a piece of bedrock. It would be cool if you did. It's pretty common in southern Wisconsin, at least, to find bits of limestone or another sedimentary rock. It's very close to the surface here in the area, but humans and glaciers especially have been moving rocks around, depositing stuff on top of the bedrock. So you are not necessarily going to find a bit of bedrock. So that concludes the video presentation for today. As always, if you have questions or concerns, please email myself or Ryan.